let us go ahead and get ourselves started. We have a lot of exciting things to go through and do today. We are going to continue with one of our examples of thinking about really for a building form, how we can go through and optimize its shape based on a couple different criteria. And we've been looking at some very simple criteria so far. We've been looking at things like, just the gross floor area and the gross surface area and thinking about how the shape affects those different parameters. Today we're really going to push ahead in terms of thinking about how the shape can be optimized to go ahead and optimize some other things. So how we can change the shape so that if we want to, for example, maximize the amount of solar collection potential, we can try different alternatives, use the Revit model to return some different values. So we'll keep on looking at this issue of how we go through and optimize this shape based on things like the solar potential on the different surfaces. But we'll also start thinking about other more complicated things. Things like, how would you actually incorporate, views to other buildings or landmarks? Our views being blocked. There's really, as we move through the last week of the class, any number of different criteria that we might be able to evaluate out of the Revit model that we want to be able to consider and just test those different things using the Revit model to see how we're performing on those different criteria. Finally, we get to the issue, and one of the most interesting issues is really how we choose, because once we have evaluations on 4 or 5 different criteria, there's a lot of different strategies about how you might choose the best overall evaluation or the best overall form based on all those different criteria. So we got a lot of cool stuff to do today. Today what we will start with is really just introducing assignment 4 to you, and this will hopefully be a fun one to work on. It's very directly related to what we're doing in class here. So if you're following along in class, I think that you should be in very good shape in terms of going through and being able to complete this like over the next week. But let me just introduce what it's all about, and then you have a chance to go through and kind of play around with some of the things and exercise them on your own. The idea is what we want to do is really go through and consider what the optimal shape of a building might be based on several criteria. So this notion of the sun and how the sun directly hits the surfaces, as well as this whole notion of viewing. Really what is the potential for maximizing some sort of desirable view, towards a river, towards a bay, towards a fantastic landmark that's off in the distance. But often as we're designing real estate, one of the criteria is that if there is a fantastic view, you want to maximize the number of offices that actually have that view. So here's what you basically are asked to do in assignment 4, and we'll lay it out in kind of distinct steps. First is really go through and just set up a building model that you can be flexing and testing. And we've included a couple different building forms for you in the assignment 4 starting point, which is out there on the coursework site. So go ahead and get that down. It just really includes some conceptual mass shapes. There's this twisted triangle mass that we've been looking at here in class. There's also kind of a twisting rectangular mass, but really you can use any shape that you want to work with. I'm not at all picky about that. So go ahead and find one that you like. And what we want to be able to do is just flex that. So what I'm suggesting that, for example, if you're using this triangular tower that we've been working with, you might want to adjust some instance parameters just to sort of set up the initial values you want to be testing, and then set up any sort of controls, any relationships between the different ones. Parameters. For example, in class, we set up a relationship in this twisting tower to give it a constant taper, where we just set up a formula so that the middle taper was half of the kind of radius at the top versus the radius at the bottom, things like that. Okay, after you've gone through and set up your shape, go ahead and add new levels to it. So add new floor levels and use mass floors to kind of add them in. And that's just going to give us the ability to compute something like the gross floor area of the building. Okay. Final thing is really just make sure you set up your project location. That'll be important in terms of accurately determining the sun's position. Okay, so please go ahead and that's just all about getting ready to go before we do anything. Next up, what you want to do is build some dynamo logic to flex one of the form's parameters, and we've been doing a lot of examples of that. So feel free to borrow anything that we've been working with in the examples of class, but you basically want to just set up a test where you can change one of the input values. I'll keep working today with the idea of changing the twist of the tower, but you can be changing the height, the width, anything you want to change about the tower. But basically, we want to set it up so that you can evaluate several different alternatives and then ultimately give an evaluation of really which of the alternatives you think is best. In terms of two specific cases that we're going to ask you to look at, one is the notion of the solar potential. And the solar potential is really very closely related to what we've been doing with all this, compute the sun and the directness to the sun. So what we'll be doing is looking at, I'll look at this with you today in class, is computing this vector between the surfaces, or quads that we set up on the surfaces, and the sun's position. And based on that, scoring the surfaces, giving them some sort of value where we can go through and just evaluate whether we think that is directly facing the sun, whether it has good solar potential or not. Okay, and we'll do that for one of the faces, we'll repeat that for all the faces. We really want to sort of understand all sides of the building, and then report these values out as a series of CSV values, so add them to the file so that we have a little collection of all the different values that we're selecting for each of the different test cases. So we'll look at that together in class today. So don't worry about that. We'll kind of go through some of the nuance of how to do that. Next up, though, we want to extend it just a little bit. Really use the same principle, but instead of thinking about where the sun is, think about where this very attractive landmark is. And really just go through and compute a directness to that landmark. So using the very similar type of logic, just put an object out there, kind of grab its location, and then using the same sort of logic for computing the directness to the sun, compute the directness to that location. Okay, and by doing that, we can actually go through and evaluate all the different surfaces about how well they can view that landmark. And so that's kind of the high-level view of what we're up to. You know, once you've gone through and evaluating those different things, what we're asking you to do is just choose what you think the optimal building shape is based on each of those criteria. Okay, so you can choose the criteria you want to use even. You know, there's two criteria. You know, one's the solar directness, one's the viewing, but you can figure out what you want to be maximizing, whether you want to maximize the highest maximum value to create one really attractive space, whether you want to have an average of all the faces, and based on all the averages, go through and kind of say that the form is good based on those averages and maximizing those. Okay, but really, you're going to choose what you think the optimum shape is based on each of those criteria, and ultimately give us a Revit model that illustrates what you think that optimal shape is for each of those criteria. So you'll actually submit two different Revit models, one that you think is optimal sun, and one that you think is optimal for view. Now, if all that is pretty easy, and in some ways it is based on what we're doing here in class, and you want to keep going, we want to always give you a little bit more for the adventurous ones amongst you. Okay, so if you're feeling adventurous, go ahead and do this. After you've determined the optimal shape, you can apply a simple adaptive panel to the shape. Maybe we'll just keep it the simple rectangular seamless panel for now, but we could put any of the panels in there, including ones that actually could respond to the values that we're measuring. Then let's go ahead and use your function that you've used to evaluate those values or create those different, compute those different values, and based on them, apply a color gradient to the panels. So the idea is that anyone can look at your Revit model of the building and really quickly see what you think the best panels are and the worst panels are in terms of the viewing or in terms of the kind of solar directness. So that's just giving us a really nice visual clue. And that's really just going to draw on a lot of the things we've done in assignment 3, when we were going through and just kind of computing color ranges based on the solar values. It's going to just be applying that to this type of building instead. Okay. Once you've devised a scheme for really kind of looking at a single criteria, okay, and optimizing for that, just think ahead to really how you would devise a scheme to actually take multiple criteria into account. And you know, there's a lot of different ways we could do that. We can do that in terms of averages or weighted averages. We can do that using different areas, and we can set up something like using the whole MacDaddy methodology of enclosing areas based on different criteria and trying to maximize the area that we're enclosing, by kind of changing those different criteria. We'll look at several different schemes for how we can do that just in the next class. But just be thinking ahead about how you might want to go through and maximize that. And then if you do have a scheme, think about how you could actually implement that logic in Dynamo to actually test that. So that's the overview of really the assignment. So at a high level, just kind of take what we're doing here in class, extend it a little bit, apply it to your own specific shape. But then if you're feeling adventurous, going ahead and taking that a little bit further in terms of trying to think about these multiple criteria and how we can incorporate those. And that's really where we'll be going for the final assignment. We'll actually have one final, hopefully not a very big assignment, where we really just think about really, given that we have a whole bunch of different criteria, how do we go through and use the Revit model to help us kind of evaluate them all together. Okay, so let me pause there for a second and see how you guys are feeling about that. Yeah, does it sort of make sense? Or go ahead and give me some comments about our questions. All good there? Anyone online? Anyone at home have any questions about that, or does it all sort of make enough sense to you? Okay, sounds good. Thank you. Okay, then let's go ahead and put that away and let's get started with actually thinking about this and some of the nuance of really how we go through and kind of start to incorporate these SUNS values and how we have to sort of adjust our thinking a little bit from what we've been doing in the past. Okay, so let me go ahead. I'm going to pop over to Revit and we'll get ourselves started. Please follow along. The session 14 example files are out there on coursework, so download them and have at them, and we'll all be working together. Let me go ahead and open up Revit, and we'll open up the example file that I'm working with. I'm working with one called example 14.1 parametric towers. And if you want to go out there and grab that, it's just hanging around there in the session 14 Dynamo example. Just open that up. Take a look at it. It'll do a little bit of flashing here, as it seems to do when I'm on GoToMeeting, but hopefully it'll come up pretty quick. It's interesting to me how, as Revit regenerates the model and GoToMeeting's trying to capture it, you really get an awful lot of flashing and kind of moving around. Okay, but we're there now. Not quite there. My little beach ball is still spinning. Okay, I think we're there now. Beauty. Let me go ahead and rotate this around just a little bit. Kind of show you what we have set up in the model. This is really just that twisting rectangular math, or triangular math, excuse me, that we've been working with for the past couple sessions. In this twisting rectangular math, we've already kind of taken it and divided it up into different math floors. So again, we did that by just choosing the math and choosing this math floors option. And within that, choosing all the different floors that we wanted to kind of put them in there. And that's giving us the ability to compute this gross floor area, because that actually is determined by the shape of the mass floors on each of the different individual planes. Okay. This is also designed, we kind of set this up a little bit different than just the standard twisting triangular math. We put a couple parameters in there to go through and link parameters. So the, what is it? The mid radius is related to the top radius and the base radius. There's a lot of different things that are sort of set up. And we did that by editing the family. If I open that up, let's see if I can get that. Oops, there's just the parameters in there. If I edit the family here, you'll see that we set up some different formula relationships just to control the geometry. We didn't need to do this. It really depends on what kind of geometry we're trying to drive for. But in this case, I decided right up front that I wanted to have, something that kind of tapered from the top to the bottom maybe for your design, you could have it bow out in the middle or kind of taper in the middle, have some relationship between the top and the bottom radius, which isn't linear, but, has some sort of interesting curvature to it. Hang on, we'll let that keep on spinning for a second. Okay, and in the family parameters, you can actually see in this case, we set up a relationship between the top, the bottom. In this case, I locked the top to 40. I could actually take that out. That was something we did when we were first testing it. I want to have that free. And then I have a relationship with the top and the bottom, or the middle radius and the middle rotation, just to kind of give it an average so it's a smooth taper. Beautiful. I can load that back into my project. Just wondering, in the edit family mode, how do you define the planes shown in the middle? Is that for the plans or the planes? And let me overwrite that. So Henry, go ahead and clarify your question just a little bit more in terms of what you're asking about. So how do you define the planes in the middle? That's kind of interesting. Actually, no worries. I could really, go into a lot of detail in terms of that. Let's go back there and see if I can kind of make it simple or relatively straightforward. See if we can get that window open. Just Revit does so much refreshing that it's a little slow just to kind of keep up. Let's see what we're doing here. Okay, there we go. Oh, no, still the spinning beach ball. The triangular one in the middle of the building on the other square planes around the building. What is the significance of it? Well, let's take a look. Let's see if I can answer that question. Yeah, really, they're all defining, different profiles that are really determining the shape. So let's see if I can open them up and kind of see what's going on. This is just like frustratingly slow to kind of like watch Revit regenerate this stuff. Okay, I think we're finally there. Let's see if we actually can, is that still open or did I close it? No, go back over here. Let's go back again. We'll open it up because it's important. We kind of like take the time and unpack it a little bit. So let's let this open. So really, this form is really based on like 3 different profiles. It's actually the same basic shape. It's just at like 3 different heights. So let's see if we can like take a look at this and see, exactly what you're asking about. Okay. So let me switch it over to an easier 3D view. This is the perspective view, which makes it a little bit hard. There's a couple of different planes you see down at the bottom, just as this is drawing. These green planes, those are the left and right center and front to back center. But then, you see there's like 3 different levels. One at the bottom, like one at the top, and one in the middle. So let me see if I can kind of flip that over to make it like a little better. Okay, so these different heights, there's one here at the top, it says level 6, there's one here in the middle at level 7, and there's one here at the bottom, okay, which is level 1. Those are just the different heights at which these like planes are drawn. So when we drew the profiles, okay, they were drawn on a plane. Like this is ultimately, just so you know, it's really just a sweep between 3 different profiles. So even if I come through and if I do this and I say, let's X-ray it, that'll actually kind of show me what it's driven by. It's not great. You see there's 3 different planes in there, these 3 different triangular planes. So what these are all about is really for drawing. Those are the work planes where I'm drawing the profiles. And those are ultimately controlled by the height, radius, the top height and the bottom height. But how that works is basically as I'm drawing profiles, for example, I'll just draw kind of a little kind of squarish profile. I choose what plane I want to put that on. And whether I want to put it on, in this case it's level 6 or 7. See if I can even pick it. Yeah, I can choose whether I want to put it on the top level or the middle level. And when I do, that's the plane. So now when I'm drawing, that profile is showing up on that plane. So if I would include that as part of my loft, it would actually include, it would sweep through those points instead. So the big thing is really those planes are really just determining, it's really the height. It's almost like when we were doing little parametric parts. We set up a lot of reference planes and we drove the geometry by moving the planes around and had things move with it. In this case, what happens is, let me kind of pop it over here to the elevations. Maybe you'll see it better over there. Okay. There's really these different planes, the one in the middle, the one at the top, and we actually have the dimensions, the different parameters for the height. They're really just driving those planes around, and that's moving around this little triangular profile. So that sort of makes sense. Okay. Thanks, Henry. I know it's sometimes it gets really mucky in terms of thinking about all this stuff. It's really there's such incredible power, but also a lot of complexity back here. And I'm not going to say those changes right now because I don't want to refresh them. So coming back over to Revit, let's talk about what we're going to do. What we are doing is we're changing that shape of the tower, and we've been changing the shape of the tower. We've been looking at logic for doing that. Okay, but we're going to do something a little bit different in terms of computing, because so far what we've been doing is taking and just grabbing very simple instance parameters out of the Revit model as it changes. And when it stops flashing, we'll open up the logic and take a look at that. You can go ahead and open up 14.1 step 1, and you can take a look at it on your end. Okay, so what we've been doing is, when my beach ball stops spinning, going through and just changing the twist, the instance variable, which is the rotation at the top. And then based on that, we've been pulling different instance values out of the object. We've been pulling the gross surface area and the gross floor area. And we even went through and computed a ratio between those things, because, again, that's kind of an interesting value. I'm going to push that over to the side. The reason I'm doing that is that'll just make it a little bit easier so we can kind of keep Dynamo open at the same time. So again, here we are. We're putting things in for this top rotation value, and then we've been pulling out the gross floor area and the gross surface area. Okay, we can look at the volume too, any of those things. Those are all values we can pull out. What we're going to do that's a little bit different now is we're going to say, hey, okay, beyond those things, can we actually look at the issue of how the sun is hitting those different surfaces? You can sort of see I have a sun path turned on here, and I even have shadows turned on. So you have a little bit of sense of what's going on with the sun and how it's hitting the building right now. But there's really 3 different surfaces on the building. There's this front face, the one that's looking closest towards us. There's the 2 back faces, which are kind of pointing away from us right now. And what we want to do is evaluate those to really figure out how much sun is hitting those, and really how is that changing based on this rotation. How can we go through and control that and evaluate that so we can actually make some decisions about how much twist to put on this building, kind of based on the sun. Okay, and again, you can be changing some other parameters instead, but I like playing with twist. So I'm going to open up Dynamo and open up that same scripting, and we'll just start taking a look at how we can approach this problem. Because honestly, when I approached it, I started approaching it kind of in a way that didn't work so well. And I want you to sort of learn from my mistake because some of my flawed logic is insightful about paths that we often go down and why we have to kind of rethink and adjust our kind of thinking. Okay, so what I'll do is I'm going to open up. Oh, where did it go? It's under session 14. This 14.1, and we'll take a look. And under 14.1, let's go ahead and start with what I call step one. That was my first attempt to kind of go down this path and, we'll kind of take a look at the basic logic and go from there. So here's the deal. If we pop on down in all this logic, down here at the bottom is exactly where we were last time. We haven't changed anything. It's really just, we're looking at the triangular mass, we're changing the top rotation, we're porting out the floor area and the gross surface area. Okay, and we've set up this nice little custom node to iterate through that. We have a little for each loop that's going to evaluate all those things and is going to return a whole series of different values as a CSV file. Okay, and they'll all be separated, so we'll have the degree of rotation, the surface area, and then finally, I guess the floor area and then the surface area. Okay, and even out of that, last time we talked a little about how you can take all those different values that came as a CSV list and break them back into a hierarchical list so you can do some computation. And we looked at how you could take a couple of different columns, divide them together to compute a ratio. Okay, so far so good. That's all the same. In terms of where we're going to start to get different now, what I want to start thinking about is this whole issue of sun and dealing with the sun. And for thinking about the sun and how we might want to approach it, it really starts with the notion of the sun has a location and we have a face and that we want to consider, and we want to think about how the sun is hitting that face. Now, in terms of thinking about how the sun is hitting a face, we can go through and look at just, the entire surface and try to come up with a single value that way. A good way to approach it is to think about really dividing the surface up into a whole series of different grids, okay, little quads, kind of like we apply panels to, and evaluating each of those. That's how we've really been doing it relative, to the stadium or to the airport concourse or something like that. So up here at the top, you'll see I've actually defined just that kind of logic. I say, let's go ahead and select a face. So I can say, let's grab that front face over here. I'll grab, do it again. I think I double clicked. Okay, so coming back into this window, what I want to do is I'm most interested in that front face. But I'm having trouble selecting it now. It might have to do with go to meeting and the overhead there. Okay, that's the face. Pop. Okay, on that face, what I'd like to do is just divide it into a UV grid. And there's some logic we've worked with in the past to say taking that face and create a surface domain out of it, then dividing it up. In this case, I'm just dividing it up into a simple grid, like, 5 by 5. We could be more fine than that. We could control anything about how fine we want that grid to be. It'll just be more computation time. Okay. We say evaluate the surface, and then we're going to get quads on that surface, and ultimately go through and do some computing of what we think the sun's directness is. Okay, and that's actually pretty similar to what we've done in the past. Let me choose the sun path there. That's currently in use. And there's this function here that takes that sun's path, says, hey, let's go through and do the normal to all those different quads and gives us back a series of values. So let's just take a look at this and then we'll run it. So if I evaluate this custom node, I'll edit it. You'll see this is that one where, again, I like to apply this scaling factor to sort of make the sun a little more realistic about the distance, but I take the sun path and some quads, I say, let's do a best fit plane, figure out what the direction and the distance between the two different like vectors, the normal to the plane and the vector that points towards the sun, see how different they are. And then in the past, what we've done is we've gone through and we've taken that list and just kind of calibrated that list. So we did that by scaling it from the highest to the lowest, so that the lowest value would ultimately equate to 0, the highest would equate to 1, and return that value. And that kind of feels okay. And that's how I started with this whole thing. I went down that path and thought, great, we'll just reuse all that logic from the past. So let's go and run it and see. Coming on over here, we will go through and set up our iteration. And to do that, I'm going to advise as you do this, go ahead and kind of start with a relatively small range of values, because in terms of figuring out whether your logic's working, you don't need 10 or 20 different values. Just 2 or 3 will probably give you a pretty good sense of whether or not your logic's working. So 20, 30, 40, that would give us 3 values to look at. That's fine. I'm just change it to 45, but it'll still just give us 3 values because I'm incrementing by 10. Let us go through and run it. And hopefully you'll see our tower dancing there in the background. What it's going to do is, again, go through and change the tower. We're going from a rotation of 20, then to a rotation of 30, and finally to a rotation of 40. And as it's doing that, it's going to do a little computation. Okay, again, getting right now those surface values. It's working away there. Oh, I think it just incremented 1. Let's let it do a second one. You see it's regenerating now. So especially with the slowness created by doing this through GoToMeeting, it's worthwhile to have a small number of values, lest you be waiting around for a long time trying to get your answers. Okay, I think it's just about there. I'm waiting for the run button to enable itself. But let's go ahead and we'll start talking about what works and what doesn't work. Overall, the notion of heading down this path works out pretty well. You know, we can get the sun's distance, we can divide it up in a grid like that. You know, that all works. We've been doing things like that, and that's pretty fine. As we go through and evaluate the sun's directness, though, I realize there's kind of a flaw in my logic. And I'm hoping to illustrate it for you, so we can actually just talk about it too. Boy, it's too painful just to watch it regenerate. Okay, well, we'll just keep talking. Well, I keep saying that, and then it keeps on luring me back into believing it's done. Okay, as you think about what we're doing with the directness values, let's kind of think ahead to really what the problem may be. The directness values that we're computing on a panel by panel basis, you know, are basically going to go through it and give us a value, you know, there's really two values that's in there. There's the raw value, which is computed, okay, and that's what it initially is returned. We go through and actually do a little scaling though. For the purpose of having a nicely scaled version that kind of had all the values spread out between 0 and 1, so it gave us a nice blend of colors and was able to control that aperture panel nicely. We did the scaling that sort of applied from the lowest to the highest and rescaled all the values. Okay, that works very well when we don't absolutely care about the values because everything's relative by doing that scaling. But actually, it turns out when you're thinking about absolute values, it's not a good thing to do. And that's really the gist of really where my initial mistake was. And again, I hope to be able to illustrate that to you if this thing ever stops regenerating. But there's a little flaw in the logic in terms of going through and scaling them. Because really, here's what I was planning to do. Here's my overall logic. And you'll see where the flaw kind of comes in. What I was thinking about doing was actually going through and for the surface, taking all the different panels and computing this directness value, okay? And then going through and computing an average of all the different directness values on the surface, okay? Do that for rotation 20, okay? Then go ahead and for rotation 30, compute all the individual values and do an average of all those values and get the average for 30. Then go ahead and do it for 40. Again, all the individual values, go through and compute the average of those things, and I'll have an average for 40. The problem and the essential flaw in my reasoning was that if you go through and scale the values from 0 to 1, okay, the average always is pretty much around 0.5. It's plus or minus depending upon how many panels you have in there, but the average is going to be right around 0.5 because you scaled them from 0 to 1, okay? And it's a slightly weighted average, but putting that, based on how many panels are high and how many are low, or if they're evenly distributed, but they end up pretty close to 0.5, for 20, again for 30, and again for 40. And really the reason is because we're doing the scaling, adding the scaling factor in there, we're almost, intentionally washing out the essential difference we're trying to capture, which is really the individual and unique difference, like in all these different variations. So what I'm going to advise is that we not use that. What we really need to do is go through and change our function just a little bit so that we're not doing the averaging, but actually going through and doing something that's a little, rawer in terms of returning the values. Now, this whole thing, and whether it's ever going to be done, is really starting to make me wonder. Is it in a loop? Is it regenerating? I'm really sort of confused about why it's taking so much time to return. Oh, well, no runs there again, but the beach ball's still spinning. Let's see if we can regain control here. Yeah, hopefully on your machines, if you ran this at home, if you ran this on your own machine, it should have been done a long time ago, and you can sort of see what the values are. Let's see what's going on with Revit here. Okay, finally. Let me see if I can pan this around a little bit. So we went through, we computed all these directness values. We have some average. You'll see the average, it just averages 0.35. That's not too awfully bad. What's going to end up happening, though, is this whole notion of just evaluating the sun's directness the way we've done it for this first instance really washes things out, because by scaling all the values, you're sort of losing the essential values. And let me kind of explain where the difference would be. If you think about this tower, okay, and let's say this is the side that's facing the sun, the one that's closest to us right now. If the values we were receiving there were between 5 and 10, the average would be, say, 7.5 on that face. Okay. On the back here, if the directness values were between, say, 1 and 2, the average on that face would be 1.5. You know, something similar kind of on the backside over here. The problem is, by scaling them all from 0 to 1, the average of all three of the sides is close to 0.5. So you sort of lose the essential difference you're trying to get out. So what I'm going to try and do is basically propose, hey, we just need to do a little adjusting and we can get ourselves out of this hole. And to look at that adjustment, let's go ahead and open up, it's the step 2. Okay, because that's where we actually implement it. Let's kind of take a look at 14.2 and show you it's all the same down in here. But we have a slightly different function here. Okay, as opposed to evaluating sun's directness, okay, which is going to return those factored values, those scaled values between 0 and 1, for this node, I defined it just a little bit differently. I said, hey, in addition to giving me the directness values that are scaled, give me the raw distance values, because the raw distance values are the ones that I'm actually sort of interested in. I really want to see that difference between 5 and 10 and 0 and 2. I don't want to see it all scaled down to 0 to 1. So let's take a look at that function, because it's really a very slight variation of what we've done in the past. In terms of these directness values, you might remember that back in the node, we went through and we had the sun path, we scaled, we go through and apply some directionality to it, then we flatten out the list and we sort the list, and this is the part right here, right in there, where we get ourselves in trouble. That's the scaling part. And that's how we computed the directness values. So what I did was actually just went through and put a slightly, this is a very small variation on the list right here. Okay, what we did is just basically take the list of all the values that are computed, and if I pull that off right after I flatten it, and instead just report those values, okay, that's actually much more interesting, the raw distance values. Okay. So in terms of doing that, okay, I got the list. The list has a whole bunch of different values in here. You know, we can go through and report them. I did one additional thing though in this formula just to make it a little bit better. Let me tell you what that is. We do have a little bit of a unit issue here. So the units that come out of the distance is a number of meters. It is a length of some type. So in order to be able to compute an average, what I'm doing is just dividing those lengths through by 1 foot, okay? And that'll basically give me a number as opposed to a length. So all I'm really doing is forking it off in 2 paths. So I'm going to get the directness value, which is scaled, as well as the raw distance value. Okay, and those are both returned as outputs. Okay, and so when we come back over here and use this in our example instead, you'll see I have 2 different outputs, the raw distance values and the distance values. And what I'm going to do is, as opposed to using the directness values, which are scaled, use the raw ones. And go through and compute that average. I'm a little confused right now in my own watching this because it looks like I'm dividing it through by 1 twice. Oh, did I just pull the values through? Let me go back over here. Yeah, it looks like I'm dividing through by 1 foot twice, which makes me wonder. I think I have something going on with the different versions that I have in here. You should only have to go through and do that once. So what I think I should be able to do is just kind of just pull that over directly to here. Because when I go through, and let me save that away, because when I go through and use it, and I get those distances back, back over here, I'm dividing those distances by 1 foot, and that'll give me a number that I could average. So a couple things there. Watch out for the scaling, and also watch out for the whole notion of you can't average distances. It's kind of weird. You can average numbers. So dividing by 1 foot really takes care of that. So let's pause there for just a second in terms of see now how traumatic that is in terms of like understanding like the basic logic and why we need to go through and make that change. See if it sort of resonates with people. So how's it feeling from your perspective? And anyone and everyone, go ahead and chime in the chat window. All good there, Henry? Excellent. So, okay, you're getting the logic of what I'm doing. I don't want it to seem like I'm just from another planet and I made that up. Okay, now, okay, so there's a little bit of a logic there. And I feel quite okay exposing the fact that, hey, my original logic was flawed. A lot of times it is. And it takes a lot of iteration to go through and get it done right. Okay, super. So this is actually kind of an A-okay way of getting started. My basic logic up here is pretty good. But here's what I got to do. I'm doing this evaluation once, okay, and once is kind of okay, but what I would really like to do is do this evaluation a bunch of times. I would actually like to do it for every variation. So because it's sort of outside of the looping, okay, it's just going to do it either at the beginning or at the end. It's going to do that evaluation once. And what I really need to do is sort of build that evaluation into my looping logic. Okay, so this thing down here, my little guy down here, which goes through and evaluates the two different parameters, okay, that's got to change just a little bit. Okay, and let's kind of show you how I change that. So the idea is as follows. If you open up that node, it looks pretty much the same. I gave it a slightly different name because the logic inside of it's going to be a little bit different. You'll see that in a lot of ways, okay, this is nothing's changed up top here. We're going ahead and setting the element parameter based on the twist. We're grabbing a couple different values for the gross floor area and gross surface area. That's fine. That's all being written out the same way. The one thing that I changed in this node was I added this other thing to consider here, which I call the sun directness for the face. Okay, and I'm adding that into the string. So in addition to reporting those first 2 or 3 values, I'm saying also give me a comma separated value, which is going to be this average directness for the face. So what I did in order to compute that was I took the logic that we were looking at over here and considering once. So that same logic, which is sort of strung out here across the top of the main node diagram, and actually put it into a custom node. Because as a custom node, I can keep on evaluating it time and time again. So we actually set up this little node called get sun directness for the face. And if I evaluate that, let's take a look at it. You'll see that it goes ahead and gets the sun path, it gets the face, it does all that domain stuff, evaluates the surface, takes that raw distance, computes the numbers there. Now that's the one, that's why I need to kind of put that back in here. Either I need to divide by 1 foot here. I'll do it over here. Well, I should do it the other way. You see how I was sort of double counting kind of in my logic here. Let's come back over here. And I do need to go through and pull this one, the one that's divided through. It really depends on whether I want to divide that either in the function or divide it after I get out of the function. Either way. Okay, so I take those raw sun directness values, I average them, I say, great, output this stuff and give me a list of the outputs. And by doing it this way and putting it inside this node, what it's going to do is, as part of every iteration, the third step of the iteration is first we get the value or set the value, then we get some values. The third step is going through and basically evaluating some strings that are going to get written out. And those strings include, as the fourth value, sun directness for face. So that's going to force this to be evaluated for each and every iteration, and ultimately just return those values. Now, in terms of writing them out, I made a slightly different version of our CSV function, one that actually takes 4 values now, but I think you guys will handle that just fine in terms of what's going on. It looks just like the one for 3 values, only instead there's a couple more strings, and we just keep on stringing value, comma, value, comma, value, comma. Okay, to put those out. So let's go ahead and exercise this a little bit in terms of understanding how it works. So let me close that up. And please, you can go and exercise it on your side too, just so it works, because I think it's going to work a lot more quickly for you than it is for me. But let's go through and see if we can make this actually happen. In view of how slow this is, I'm going to actually just have it iterate for a single value or maybe 2 values, because it's really, it takes so long to iterate through on my end that, I just want to sort of speed up and give you a result pretty quickly. On your end, go ahead and you can leave it 20 to 50 or whatever it is, because you can kind of have it iterate several more times. But I'm just going to say 20 to 25, which will really just iterate for a single value. Okay, so I just want to sort of see what this value looks like as it comes on out. That make sense? So what I'll do is go through and let's run it for just a single value. So a little flashing over there. So again, it's still going to get the surface area, it's going to get the gross floor area, and now it's going to return its some average of these directness values all across that face. Okay. Actually, that wasn't so bad. That was pretty quick. Actually, if you want to even see in here, let's kind of roll this out. You can actually see in the preview really what it's doing in terms of taking that face. Oh, it looks like I have the back face selected right now. Okay, and computing those values, or I might be just reoriented a little bit differently. But you see all the different quads and the points that it's using to determine those, and it's evaluating that surface. In terms of the result, let's take a look at that. I'm watching the file. So you can see for the currently selected face and this rotation, it's returning a value of 0.88. Okay, let's go ahead and test this just a little bit so we can sort of get a sense of how the function works. And we can do that. I'll just go ahead and kind of test it on a couple different faces. So let's go ahead and for get sun directness, let's try different faces. Okay, so I can say, let's take the face, and I'll choose the face that I think is being the most in the sun. This one right here. I'm sort of guessing that based on the way the shadow is going. Okay, let me go ahead and run that. Yep, you see it's oriented a little bit differently than I think. Okay, that was one face. Let's go ahead. I'm going to change, and maybe if I go, I'll think of it in a clockwise direction. I'll get that, what I consider to be the back face over there. I'm going to select that again because I'm not sure I quite got it. Okay, I'll think of that as the back face, and I'll run that. Okay, looking good. And now we'll do one last one. We'll do the face, which is this one over here. Okay, and we'll run that one. You can sort of see the little preview window up there. Keeps on changing itself as we're looking at the different faces. Yeah, just kind of saying what the surface is that's being evaluated and showing you the points on that surface. Okay, looks like we're done. Let's go back to the overall environment. This is called the home, kind of in our Dynamo environment, and take a look at those different values. You'll see that for the first one was the one we ran before we tried all three tests. Yeah, for the first one we ran after we started trying, that front face, the one that's closest to the sun, the way I think of it now, has a value of 1.57. The one that is, as I rotate clockwise, it's kind of on the upper left corner. Okay, that has a value of about 1.9. And the one that is relative, you can see it's in the shadow. The one that's over on the upper right-hand corner, that has a value of 0.88. Okay, so this is kind of confirming my intuition in terms of which side has the highest value, which side has the lowest value. So just got to keep that in mind as we go through and work with these different values. The way we've defined our logic, kind of a higher value means that it's more directly in the sun. Okay, and what we really want to do is be able to go through and say, great, these are fantastic values, in terms of like this individual faces being evaluated separately. Could we actually go through and evaluate all three values, all three faces at the same time, so that for any different instance of twist value, you get a valuation of all three of the different faces, face A, face B, face C. Okay, and that's really where we're going to go next. So let's do this. Let's go ahead and break for about 5 minutes. For anyone who wants to stand up and grab some water, I'll kind of start the recording again in terms of what's going on, give that a chance to clear out. But if you rejoin me in about 5 minutes here, we'll continue with how we actually get several different values from several different faces together. Okay, and then we'll talk about really, once we have all those different values, how do we make a decision? Okay, so let's go ahead and break very briefly now, and we'll be back in about 5 minutes.